Hi everyone, I'm Ardozunolu and I'm a sophomore undergrad at Johns Hopkins University and also one of the co-authors of our paper titled The World is World, How Many APIs? A Thought Experiment. As you can tell by the title, it's more of a thought experiment rather than an empirical study. So what are we thinking about? Before jumping into our thought experiment, we can start with the embodied language models. Large language models, even though arguably are recently shown to be effective planners within both virtual and embodied simulations, and the way they interact with their environments is usually through the states and actions. However, the current simulators and resources on agent-based planning and execution have a very small action space, which puts a natural upper bound to the uh, agent's ability to interact with the environment. The current resources we have also do not cover a wide range of domains, and they are usually limited to a single domain. And another issue with the current resources we have is that they usually have an inconsistent granularity of actions within their action spaces. This creates a disparity because low-level actions are motor control actions that can be directly executed by the agent, whereas the higher-level actions still can be decomposed into a chain of lower-level actions to be executed. And coming back to our thought experiment, this is why we are thinking about what constitutes an ideal action space for simulations and grounding instructions into the real world. However, an important caveat we have is that we ignore the implementations of these actions in order to be free of any limitations that arise due to the technical constraints. Therefore, we aim to create a hypothetical action space to approximate the size of the ideal action space for simulations and grounding instructions. First, the ideal action space must consist of a wide range of actions that are applicable to an extensive set of scenarios and tasks. We need such a wide range of actions to better enable the agents for executing different tasks and prevent them to be restricted to a narrow set of capabilities. For example, in this case, the model doesn't really know how to handle the action of wipe since no given action in the action space is similar or corresponds to wipe. The ideal action space must also cover diverse domains because real world is obviously more than a kitchen, which is usually limited to cooking. And again, a more diverse group of domains would better prepare the agent for a wider and more realistic set of tasks to be executed. And coming back to our example, the model cannot generalize beyond the kitchen domain well and cannot really handle working with a seed. The ideal action space should also have a consistent level of granularity to ease the communication with the agent. And lastly, the action space shouldn't have repetitive actions. If we already have an action that satisfies a requirement or fulfills a function, then we probably don't need another action that does the same thing. And this is why we propose the world APIs. World APIs are atomic actions that correspond to a cycle of the intelligent agent. Using the world APIs, we conduct our thought experiment and approximate the size of an ideal action space that covers a wide variety of domains with a consistent level of granularity. So unlike previous related work, which takes a bottom-up approach and initially defines an action space to collect associated instructions and then generates the programs, we instead take a top-down approach and collect natural language instruction sets from wikiHow and induce new actions that we call APIs to generate Pythonic programs by few-shot prompting GPT-4. And to ensure our diversity of the domains, we pick the home and garden category from wikiHow, which itself contains the subcategories such as gardening, cooking, crafting, housekeeping, and so forth. And to achieve a consistent level of granularity, we simplify our environment by omitting some details such as spatial and scenery details. Due to this simplification, we introduce the base APIs that can be seen here, which are assumed to direct the agent accordingly. We also avoid motor control APIs, which are excessively low level to the point that they prevent the induction of new APIs. And we do so since our aim is to create an action space with various actions. Similarly, we avoid overly general APIs, and our reasoning is that um, it would degenerate the task of agent-based planning and API induction into semantic parsing, which is not really concerned about grounding actions and instructions into the real world, whereas it's the primary topic we are interested about. Therefore, we implement an affordance-based approach instead. Since we are not limited by the restrictions of a simulator and also since we define a hypothetical text-based environment, we don't really have to adjust to any confinements regarding the action space. And therefore, we can create an extensive action space with iterative API induction. For our iterative API induction, we first gather 1,000 instruction sets from wikiHow, and then we annotate a group of instruction sets manually to use them as the seed set for induction. And after that, we build a prompt to be given to GPT-4 by concatenating in-context learning instructions and in-context learning examples, which consists of programs from either the seed set or previously generated programs. The goal at this stage is not just to induce new APIs, but more importantly, generate the programs to represent the input instruction sets. And if the output program is syntactically well-formed, then we append our API pool with the new APIs and our program pool with the generated program. We evaluate our pipeline with two metrics, redundancy and faithfulness. Redundancy refers to how replaceable the given API is in comparison to the already existing APIs, while faithfulness is how successful the output program is at executing the instructions. Both of these metrics are computed based on the human annotations of the generated output programs. Our baseline is simply instructing GPT-4 to output the program based on the input instruction set. We then expand our baseline by introducing the in-context learning examples for the already existing APIs to help GPT-4 better understand the concept of APIs and how to use them. As you can see, in-context learning examples help reduce the redundancy by a small margin. And lastly, we utilize the instruction descriptions from wikiHow to further improve our pipeline. They also bring the redundancy down, but we believe we still have a room for improvement regarding the redundancy. And similarly, inclusion of in-context learning examples and action descriptions also improve the faithfulness, whereas in-context learning examples by themselves degenerate them slightly. Although we have a room for improvement regarding the redundancy, we believe it's feasible that the induction rates get slower and lower as we run our pipeline, which implies that we find a stable action space that is capable of covering new tasks without inducing new APIs. Here you can see the most frequent 50 APIs. They come from diverse scenarios and are not saturated in a single domain. And now you can see the contrast between the world APIs and related work. The world APIs that have a similar action in related work are colored with purple, whereas the unique world APIs are colored with light blue. At the end, our approximation leads to an action space that consists of more than 300 unique actions. You can see how and where the world APIs stand in comparison to the related work. However, we believe it's definitely important to keep in mind that our experiments were conducted over only 1,000 instruction sets from wikiHow, and they are just less than 0.5% of the wikiHow, which we deem to be the proxy of the real world. So in summary, we did an approximation of the ideal action space for agent-based planning and execution. Our goal was to potentially guide the future work to help them uh, build a more inclusive and better and more extensive action space for intelligent agents. To do so, we built a pipeline to convert natural language instruction sets into Pythonic programs, which we then leveraged to generate the world APIs. These world APIs cover 1,000 instruction sets and real-world tasks in the form of Pythonic programs and help us find the ideal action space we are looking for. So this wraps up our current work. Thank you for listening along. And if you have any questions, please do not hesitate to ask it now or reach us.
Are there any questions from the audience? I have a question. So, so in the world APIs that you learn, do you also represent the preconditions when those atomic actions are applicable?
Yes, we merge the interactable objects into a class named world object, and those world objects contain materialistic and actionable properties, and we consider those conditions and properties in our programs.
Thank you. Any other questions? Okay, let's thank the speaker.